In the world of data, there's this massive debate that's been raging for years. What's more important, getting the right answer or actually understanding why it's the right answer? And look, this isn't just some nerdy technical question. It's a fundamental clash of philosophies that shapes everything, from your social media feed to how we discover new medicines.
So let me just ask you, right out of the gate, imagine you've got a mountain of data in front of you. What's your top priority? Is it just getting the prediction right no matter what, or is it digging in to find that genuine understanding? This single question, that's the great divide we're going to explore.
Okay, so this whole debate, it's not new at all. Actually, it was laid out perfectly back in 2001 by this absolute legend in statistics, a guy named Breiman. He wrote this incredibly influential essay called Statistical Modeling: The Two Cultures, and it basically drew a line in the sand, exposing this deep split in how people were approaching data.
And the funny thing is, the basic tools like regression, they've been around since like the 1800s. But what Breiman was talking about was this really modern split, one that was supercharged by the rise of serious computing power. And what's happened in the 2 decades since he wrote that essay, well, it's a really cool story about how these two worlds have started to come together.
So let's talk about the first camp. Breiman called them the data modeling culture. For these folks, the #1 goal is to understand how the world works. They believe that underneath all the messy, chaotic data, there's a simple, beautiful structure, a kind of formula that explains how things are connected, maybe with a little bit of random noise thrown in. Their job is to find that elegant formula.
The best way to picture this, think of a super detailed architectural blueprint. The model they build is designed from the ground up to be readable, to be interpretable. The whole point is clarity. You can look at the blueprint and understand exactly why the building stands up.
All right, and then you've got the other side of the coin, the algorithmic modeling culture. For this group, understanding is, well, it's nice if you can get it, but the holy grail, the only thing that really matters is predictive accuracy. They build these incredibly complex functions that can take some data in and spit out a prediction with pinpoint accuracy, even if what happens inside is a complete mystery, a total black box.
And the analogy for this is just perfect. It's your GPS. Think about it. Your GPS gets you to your destination perfectly. It's insanely accurate. But does it teach you the layout of the city? Does it help you build a mental map so you can get around on your own? No way. It just gives you the right answer turn by turn.
So, okay, let's really put these two philosophies head to head. On one side, you have the data modelers. They're all about understanding using simple, clean tools like linear regression. They operate on the belief that we can actually figure out the true process behind the data. On the other side, you have the algorithmic modelers. They're chasing raw accuracy with these complex beasts like random forests. Their philosophy? The real world is way too complicated to model anyway, so let's just focus on what works.
So, right around the time Breiman was writing this, something huge happened that completely tipped the scales in favor of the algorithm guys. Big data. All of a sudden, we were drowning in data sets so massive and messy that the simple, elegant models just couldn't keep up. And that's when the black boxes really started to take over.
And Breiman himself just nailed the description of this approach. He said, for this culture, the inside of the box is complex and unknown. Their entire goal is just to find some function, some algorithm that works. That whole mindset, it was tailor-made for the era of big data.
This right here, this is the classic way of thinking. This is the data modeler's world. They believe that all those scattered dots are just noise. Their whole job is to ignore that random mess and find the true signal hiding underneath that smooth, clean black curve. But, and this is a huge but, here's where the traditionalists ran into a wall. When you threw these massive modern datasets at them, think millions of credit card transactions or entire genomes, the complex algorithms, things like the random forest, which, by the way, Breiman himself invented, they just won. They were flat out more accurate.
And this brings us to Breiman's really radical, almost heretical idea. He basically said, let's flip the whole scientific method on its head. Don't start with a simple theory you understand. Instead, build the most accurate predictive model you possibly can, even if it's a black box. Then, use that model to try and figure out what's actually going on. Accuracy first, understanding later.
So you can imagine, this just created this massive philosophical battle. The algorithms were winning, there was no doubt about that. But at what cost? I mean, what good is a perfect prediction if it doesn't teach you anything new about how the world actually works?
And this really gets to the heart of the matter. I mean, think about it. If you build a black box that can predict the weather perfectly, down to the minute, but it can't tell you anything about why a hurricane forms, have you actually done any science? Or have you just built a really complicated machine that mimics nature without explaining it?
But then, just when it looked like one side was going to win, something really cool happened. Instead of one culture wiping out the other, they started to merge. The traditional statisticians decided to take their tools and use them to pry open those black boxes.
See, the statisticians didn't just throw in the towel, no way. They just expanded their mission. They took the incredibly powerful and accurate algorithms from the other culture and started treating them like a scientific subject, applying all their rigor to figure out what was really going on under the hood. Let's take random forests, for example. Statisticians came in and made some really clever tweaks to make them more reliable. First, they found ways to stop the individual trees from getting obsessed with tiny, meaningless patterns, which made the whole model way more stable. Then, they figured out this brilliant way to split up the data to prevent the model from basically tricking itself. And finally, they changed how the model samples the data, which was a massive breakthrough because it allowed them to build a real, formal mathematical theory around it.
And all this new insight, it led to some serious upgrades. For instance, the old methods for figuring out what's actually important in a model, they had some major flaws. They could get totally confused if two variables were related, and they'd tell you both were important when maybe only one was. The new methods that came out of this research are way smarter. They can actually separate the true signal from the noise. So fast forward to today, and that great divide that Breiman wrote about, it's mostly been bridged. The two cultures have learned so much from each other, but that doesn't mean the story is over. Oh no, the debate has just moved to a new battleground.
And that new battleground? It's deep learning. The neural networks we have today, they are the ultimate black boxes. We're talking orders of magnitude more complex than a random forest. They can do things with images, text, and sound that seem like magic, but trying to understand how they do it is one of the biggest challenges in all of science right now.
You know, it all comes back to what Breiman was hoping for. He ended his essay by saying he hoped the field would return to its roots of just working with data and testing ideas against reality. And you could argue that this blending of the two cultures is exactly that, a return to a more pragmatic, problem-focused, and powerful way of doing things.
And that leaves us with one final, really big question to chew on. As these algorithms get almost unbelievably smart, are we actually learning more about the world, or are we just learning more about the weird, complex tools we've built to look at it? The answer to that question is going to define the next chapter of data science. Thanks for tuning in.